Okay, having dealt with a single frequency and a pair of frequencies, we can now tackle an infinity of frequencies. We're going to look at a Gaussian wave. So we're going to write down our Gaussian wave as some function of x and t, and that function is e to the negative a squared x minus ct all squared. So a determines the width of our Gaussian, the width is 1 on a, and the speed is given by c, so c up here. Now, to find the behavior in Fourier space, let's start by finding the transform over k at time equal to 0. So we're going to set t equal to 0 and just take the Fourier transform of this function, which will be this function just of x, and then we can use the shift theorem to see how this thing propagates in time. So at t equal to 0, this bit goes away, and the Fourier transform we're finding is just the Fourier transform of the Gaussian e to the negative a squared x squared, which we can just write down. It's a Gaussian in k space, so it's a Gaussian as a function of k, noting that as the Gaussian in real space becomes more narrow, the Gaussian in k space will become wider. So this is what I've drawn here in this graph here is the Gaussian in k space, and what we need to do now is make this whole system move as a function of time. So we know that each k component rotates at a speed e to the negative I omega t, and the amplitude of each k component is given by this function here. So this is the amplitude along each position of the k-axis. And at each position on the k-axis, we're going to start rotating that component around at e to the negative I omega t. And without dispersion, we know that omega is equal to k times c, where c is the speed of the wave. So each one of these components here will be rotating at a speed proportional to k. So let's see what this is going to look like. Here's the wave moving slowly in x, and here are all the components in k space rotating around at different rates. The further you move away from k equal to 0, the faster the rotation. And so in k space, this thing is winding up into a spiral as the wave moves along. Okay, so let's continue along with our calculation here. So if we know that each of these k components rotates at this speed, e to the negative I omega t, we can write down the function fk of t, that is this function that I've animated here, as fk at time equal to 0, e to the negative I omega t. Replacing omega with k times c, where c is the constant speed of the waves, we can write that f of k and t is the Fourier transform at time equal to 0, and then each k component is shifted, rotated in the complex plane by this complex exponential here, e to the negative I k c times t. So this is the thing which I've animated here, and this is the function that I've animated here. But from this point here, we can actually go back and find the function of x and t, because this is now the Fourier transform, f, k, and t. If I take the inverse Fourier transform of all of this, I should get back the function f of x and t. So let's apply the inverse Fourier transform. That would be 1 and 2 pi, then we integrate over the entire k-axis, and this is our function here, which is the Fourier transform of our wave, and then we integrate it up with this kernel e to the I kx. And so this is now our wave expressed as a sum, or rather an integral, over all the different k components given with these amplitudes here, and this phase shift here, which depends on the distance that the wave is propagated, or the time for which it is propagated. And so this is the shift theorem again, in other words. So here we've just dealt with a system with an infinity of frequencies and an infinity of k vectors, but the ratio of omega and k is constant for all frequencies, so all the frequencies have the same velocity and the pulse does not change shape.